in which case we need flaring system. Flaring system is those flares that you can see in most of the petrochemical or refinery plants, so that you can see a flame of fire is just, I mean, there is a flame of fire that you can see it even from a long distance, far away, I mean, very far from that plant. So this is mainly designed to, in case that we have overpressure in our system. So overpressure can be due to some external fire. We have one of our equipment catch fire and we cannot run it anymore, so we have to close it. If there was a gas line going to that equipment, so now we have to stop that gas line, and if the gas is accumulated, we have to increase the pressure in other equipment, so we have to release it. Second, blocked valve. So if there is a valve which is blocked and it leads, let's say, the outlet of one of the reactor, which is a pipe, so it has a valve, that valve is blocked. So now the pressure in the reactor increases and we have to relieve that pressure. So what we do, we have a pipeline that we connect it to the flare and we send that gas to the flare. We either burn it, that is the most of the time that we burn it, or we just relieve it as a cold gas. Then process abnormality, maloperation. So if there is some maloperation, abnormal operation, so in this case we use flares. Equipment or service utility failure. So if there is one of our pumps is failed or compressor is failed, so we might have overpressure in some equipments. Change in the ambient condition, stormy weather, very hot weather, very cold weather. So those are all the cases that we can have some failures and that can cause overpressure. Runaway chemical reaction. If the reaction run away, this is the case most of the time in nuclear plants. So in that case, we have to also depressurize the reactor and send the excess gas out of the reactor, so we can use some flaring or pressure relief systems. So in general, they are used, the flare systems are used to destroy the flammable, toxic and corrosive vapor. So if we have a flammable vapor like hydrocarbon or toxic and corrosive vapors, so what we do, we usually use the flaring system to burn these gases and then send it to atmosphere. And also some gases that are coming from relief valves, I mean the safety valves, and also from emergency venting. So we send them to the flare and we burn them. So what is flaring? So in this figure below here, you can see how flaring system works. So we have different type of process system. It can be, let's say, a heat exchanger. It can be a reactor. And or any other type of process system. So they are all connected to such a piping network that we call it flare heater, and even this piping can also call flare heater. So in case that any of this equipment they fail, we collect the excess gas from this equipment. First, we send them to a flare knockout drum. So this knockout drum is to separate liquid from gas. So if we have any liquid coming from this piping, so we send it first to the knockout drum. This is knockout drum. So you have the explanation in the notes of this slide. Then you use this knockout drum to separate gas from liquid. Then you will send the gas to the to the flare system, and you usually burn it. So is a combustion control process that we use to burn the waste gas remotely, and is usually elevated. So is usually the flare, especially the tip of the flare, is elevated and is located at a very high, is located at a higher level than ground, so that it burns the flame open in the air. Then so we have, like, even designing such a flare system has a very special design. So the tip has a special design. Auxiliary fuel, sometimes we need to use air to burn this gas, so we inject air through to the flare as well to burn the gas. Or sometimes the gas that is coming from other equipment doesn't have enough pressure to go up through the flare, so we use let's say steam or air to just mix with this vent gas, this excess gas, and we send it to the flare. So we want, if in case we want to burn the gas, we usually want to have more than 98% of that gas to be burned. Then the flaring process, the flaring process can also produce some byproducts that we don't like. Let's say SO2, NO2, carbon monoxide. Those are undesired gases that we don't want. So this can be due to mal-ignition or mal-burning, mal-combustion. So we have to improve and modify the design. So it usually can, most of the time, it can produce a big amount of noise or sometimes a smoke if the combustion is not completed, and also radiation. So in installation of the flare in the plant, and the location that we want to install it has also some specific procedure that we have to follow to minimize the effect of each of this problem in the plant. Then again, what is a flare system? It's a safety device if we have excess gas in the process, excess hydrocarbon gas. This is in the case of natural gas processing or refineries. So before we send it to the air, we will burn it in the flare and then we will send it to the air. Why we do that? Because hydrocarbons like methanes, if it's burned, it will be converted to CO2 and water most of the time, which is less dangerous to send it like methane to the air. So it's better to burn it and produce this product and send this to the air than sending CH4, because this has a higher potential to react with other gases in the air, and it can produce more dangerous products than only CO2. Then, so hydrocarbons are flared. So this is one alternative to release this these gases to the air. So if we don't have anything to do with that gas, we cannot use it in the process. So we release it in the atmosphere. We burn it most of the time. And so as I explained, exposing those excess gas like hydrocarbons, like methane, to the atmosphere before combustion can be more harmful than if we burn them and then we send it to the air. This is one example that I am showing here. Hopefully it's clear so far for you. So, some additional information about the flare system. no need to repeat all of them. So sometimes the process vessels, the process equipment, they undergo to overpressure that we have to manage it. So we usually have safety valves and rupture discs. You will see about these two parts mostly in Unit 5. So these valves, they are adjusted when we have let's say a vessel. Just let me clean this part. So when we have a vessel, so when we have such a vessel, it can be a reactor. We can also design a safety valve or rupture disc. So if the pressure in this vessel goes up, so this valve take action and will open and it will release the gas from the reactor. So those are the safety valve and rupture discs that prevent the equipment to reach to very high pressure like this reactor here. So then what we have to do with this gas that is coming out from this safety or ready valve? So we have to do something with it, right? So the best option is to send it to the flaring system, and either we release it like that or we burn it. That in most of the case we will burn it. So okay, most of the time the gases that are released from the process plant are dangerous. So we have to burn them first and then send it to the air. So this is better than just sending to the air without burning them. And emergency venting. So gases that are released due to emergency venting, like the example of reactor here. So we also send them to the flaring system and we burn them. Okay, so design factor of flaring system. So there are some factors that we have to consider, and it's mainly for safety and environmental concerns that we have. So the factors that we usually consider is a smokeless operation. We don't want to create any smoke. Flame stability, so we want to always have the flame. We don't want the flame to turn off for any reason. You know, windy, stormy condition, we don't want the flame to be gone. We want it to be always on. Flare size, capacity, stack time, so how much gas in worst scenario the flare is receiving. Okay, so this is the flare capacity, how much gas the flare has to burn in worst scenario. So if we calculate this when we are designing the process, then we can calculate the size of the flaring system. I mean the diameter, the height, that's the height. So all of this can be designed properly based on the capacity if it's known. Then thermal radiation. So as I said, the flare system, it will produce a big flame. So that can also produce a big amount of radiation. So if let's say we have, and that's my flame here. So let's say if we have people working around the flare, so this radiation can affect them. So we have to calculate it properly. Noise level, it can also produce noise. So if people are working around it, so that will be problematic. Reliable pilot and ignition system. So like this part here, this part is the ignition system. So we cannot send someone, or even this part here. We cannot, I'm talking about the ignition system, this part, which is this too. So we cannot send someone up to the top of the flare and we give him a lighter on, I don't know, a match to turn on the flare. No, it doesn't work like that. We need this automatic system to do it for us. So this part here is like a big lighter that can turn on the flare. So even the design of this equipment has some specific procedure to be followed. And also Flashback protection is when there is, like change in the weather, windy weather, so we don't want to have flashback. So we can also design the equipment in the way to protect it. Flare tip, burner tip is all located here. And also purge. Sometimes we need to purge gas, which this is what I will show in the next slide. So what we have in our flaring system, we have the flare gas, which is, let's say, hydrocarbon coming from any process equipment, is collected in a knockout drum. Then it will be going to the flare system. Here, most of the time, we need to mix it with some gas. Let's say it can be air, it can be a steam, to increase the pressure and make sure that this gas is going out of the flare properly. Or we need some combustion agent, like air that has oxygen, that can help us for oxygen. So this goes through this gas seal, this part. So why we have this cap? Because if we don't have this cap, this gas can go directly to the top, to the tip of the flare, and it will decrease the efficiency of the flare. In that case, the gas might leave the flare without combustion. So we keep this, so this gas can go through this cap, so it will spend more time in the flare. Then it goes slowly out of this part, and here it is already mixed with air. Then it moves all the way through this part, the flare tip, and it will ignite at the top. We have also a liquid drain here. Why we should have such a drain? Because the hydrocarbon that is coming from the gas that is coming out from knockout drum, which is located here. Knockout drum is somewhere here. Then we send the gas to the flare here. So this gas might have some liquid. So this liquid can go through the flare with this gas. So we can collect that liquid by using this liquid drain. Or even if for the sealed gas injection, we might use a steam, that steam might condense. So it creates some liquid that we have to collect it. We are talking about this part here. Knockout drum. So they separate gas from liquid. Okay, this is the first function. Then since they separate the liquid from gas, so they prevent the liquid to be discharged to the atmosphere, so they will collect them. So if we have liquid phase in the gas that is going to the flare, it can produce a smoke. Okay, so we can reduce the amount of smoke by separating liquid in knockout drum. So if we have less liquid in the flare corrosion, we have less corrosion, we have less damage to the flare tip, so the flare tip life will be more. And so by using a knockout drum, we will drain the liquid before either sending to the and we will drain that liquid. And what we will do with that liquid, we either dispose of that, we dispose that liquid, or we use it and reprocess that liquid and use it in some other type of, in another part of the system, of the flare system. So this is important. Oops, I don't know why my star become like that. So this is an important figure that you need to know. We have our gas are coming from different equipments. Sometimes we need to add or remove some gas by purging. Most of the time is adding. Sometimes we need to add, or sometimes we need to remove. Then they are collected to the knockout drum, flare header. Even this part is called also flare header. Okay. Then we send it to the flare. Flare has, those are the main part of the flare. The bottom part is liquid seal, that we collect some liquid. We collect some liquid at this part. Flare stack, molecular seal that you saw in another photo. How does it look like? Then we have the flare tip pilots that is usually used to ignite the flare, and sometimes we need to add steam or air to help to burn the gases in a more efficient way. So this figure is important. Try to memorize it. Okay. Now some additional information about knockout drum. So knockout drum, they are located before the flare stack. So this is obvious that we can separate the liquid from gas, from excess vapor that we have. Then the excess gas, okay. So the knockout drum can be horizontal or vertical. So you will learn about this knockout drum more in your other course. Is PO 2410. So in this course that I'm now teaching this semester, you will learn more about the knockout drum, vertical, horizontal, and then after that they will go through the flare main heater. So main heater is after the knockout drum. So the liquid collected will be pumped to another tank, so it can be reused or we dispose it. So the gas from knockout drum, then it goes to the flare stack, and then the liquid seal can collect some of the remaining liquid from the gas, and then after that it will be burned. So molecular sieve. So this slide is explaining the previous figure in slide 13. Okay, so it's just explanation of those equipments, and it tells you what we have in each step. So molecular sieve, what it does, it provides a seal against the entrance of the air, so it doesn't let the air to go through the flare, and it minimizes the possibility of some issues like explosion of the mixture inside the flare system. So that's also another importance of molecular sieve that we have. Then okay, flare type. The flare systems, I'm now talking about this part, is important. Flare systems are categorized in two ways. So height of the tip of the flare. Tip of the flare is the toppest part of the flare. So the height, how far it is from the ground, if it's like close to the ground or it's elevated. So that's one of the categories. One of the way that we categorize the flare. And another method that we categorize them is the method that we enhance the mixing at the flare tip. So we can use steam, air, or some pressure, or non-assisted. So those are the methods that we use at the top of the flare tip. We can use air, steam, or some pressure source and mix it with that gas at the top of the flare, or we might not use anything. The flare gas is enough at high pressure that can be burned easily at the tip of the flare. Then so there is advantage and disadvantage in each of them, ground or elevated flares, that I'm going to talk a little bit about them here in this part. So elevating the flare, so if we elevate it, if we install the flare tip at a higher level, so we can, what we can do, we can prevent any danger from, you know, like radiation. So if there is a big flame, it can produce a high amount of radiation. If we install it at the top, at higher elevation or higher level, so this radiation effect will be less. So it will be less dangerous for the people that are working in the operating area in the ground level. And also how we set that height, we do some calculation. For the worst scenario, we calculate the amount of gas that we will send to the flare in the worst scenario. We calculate the amount of radiation, and then based on that, we decide to choose the height. So another important term that we have to consider is that when we combust the flare gas at the top, so this gas it can be sometimes NO2, sometimes it can be H2, sometimes even it can be NO2 or carbon. Let me clean this. It can be carbon monoxide. So those are dangerous gases. We don't want the operators to be in contact with these gases. So we will, so if we release the flare exhaust gas at the higher level, so the possibility of this gas to go to the ground, to be in contact with the operators, will be less. So, and also we can avoid the noise, the effect of noise, heat, or the smoke, or even bad odor, okay, to the operators on the ground. Okay, or as I said, the pollutants, the gas going out of the flare are pollutants, so we can release them at higher elevation to reduce their bad effects on the operators or in general to the society living around the plant. Okay, another concerns that we have to, another concerns in designing the flares is the smoke. You might have seen some flares, they create a smoke. So this is most of the time because of the malcombustion or the oxygen efficiency is low, so there is no enough oxygen for the hydrocarbons at the tip of the flare here to be burned completely, so it will create some smoke. So another thing is that cracking means breaking the molecules, large molecules of hydrocarbon to a smaller one. So when cracking happens, we can have some hot and a small particle of carbons that they can create those smoke. So like it's when those hot and a small particle of carbons, because of the oxygen deficiency, they cannot be combust completely at lower temperature, and they can produce that smoke. Non-assisted flares, the flares that we don't use any air, any steam, or any ignition agent, they are more eager to smoke. Okay. I think there was some mistake. Yeah. So it has such a configuration that we have, it has all those components that you have already seen. We have our heater, knockout drum, then it goes through a liquid seal. It can be at the top. It can be, the liquid seal can be inside the flare or outside, as you can see here, to remove some liquid condensates. We have flare stack. gas barrier, so is the same as like molecular seal. Then at the top we have flare tip that we can mix it with some, we can mix the hydrocarbon gas here in the flare tip with some steam. That the steam line is also located here. So this is a kind of a general configuration of a steam assisted flare. Then we have okay, there are several steps in designing the flare system, so I'm just gonna talk about them. So first of all, we have to identify the system, okay, which type of system we are, which type of protection system, relief protection system we are dealing with. We have to identify the cases for overpressure, which condition we will have severe overpressure. We have to consider the worst scenario. Set pressure, for, let's say, for the reactor that I already gave you the example. So once for each equipment like reactor that we have gas phase, we have such a safety or relief valve that when the pressure increase here, we have to, this valve comes to the action and it will release the gas that goes usually to the flare system. So how how we design, what's the set pressure of this valve? Let's say if the maximum pressure that this vessel can withstand, can tolerate, is 100 bars, so the set pressure of this valve can be, let's say, 80 bars. Once the operating pressure of the reactor is usually, let's say, 30 bars, something like that, or even more. It can be 50 bars. So what does it mean? The set pressure means that we have operating pressure, let's say, is 50 bars in the reactor that is operating at 50 bars, and this vessel, this reactor, can tolerate pressure up to 100 bars. After that, it will have some operating problem. It might explode. So what we do, we set this valve, this safety valve here, at 80 bars, which is far below the 100 bars. So once the pressure in the reactor reaches to 80 bars, which is usually more than the normal operating condition, not usually, all the time, more than the normal operating condition. So this valve is set in that pressure. So if the pressure reaches to 80 bars, it comes to the action and it opens the line and it purges the gas that usually goes to the flare. So this is the definition of the set pressure in this case. Okay, determine controlling load for each relief. So how we control this valve? So it has to be determined. It says like is it like manual? Is it like automatically by using electrical motors or hydraulic valves, or it can be any type of the valve. So the controlling is also important. Okay, for the flare, we have to consider all the source of emergency relief, and we have to consider the worst scenario, and based on that we have to calculate the height and diameter of the stack of flare. Then type of the flare tip and seals, which we have different type of flare tip that has to be also considered. So as I said, we have to estimate the worst scenario, that we have to know like what's the maximum capacity of the gas, flow rate of the gas that will be sent to the flare, and based on that we will calculate all these specifications, which is like the diameter, height, the flare tip, seals, and so on. And at the end, the piping and PNID layout, that is for whole feather system, including all the connections from the equipment, let's say like heat exchanger, reactor, up to flare. So that's one thing about the flaring system that we need to, I mean, like those are the design aspects that we need to take into consideration. Next, we have, determining the load on the flare. So as I said, we design the flare based on the maximum capacity, or worst scenario, that all these safety valves, they come to the action. That's worst scenario. That is when we have overpressure in vessels, we have some operating problems like external fire, abnormality of mal-operation. We already talked about this slide before, it's just kind of revision. And some failures in this equipment, utility services, and so on. Change in ambient condition, like a stormy condition or very cold condition, they are all, all this can lead to a mal-operation. That has to be taken into account. And runaway reaction, that this happens most of the time in nuclear plant, but in reactions that they produce high amount of heat, highly exothermic reactions. So when we have a runaway reaction, that can lead to increase in the temperature of the reactor, and most of the time it also, the heat which is generated in the reactor will increase. So we will have a high temperature in the reactor, and this high temperature can vaporize the liquid. It can also, if the reaction is a gas phase reaction, pressure will increase rapidly, and we have to relieve that pressure, that we use some sort of safety valves to do so. Okay, so the pressure will increase highly. So once we calculate all this load coming from different sources, then we can list all these sources, do some calculation, and see what's the maximum capacity of our flaring system. Maximum capacity of our flaring system. So this will be calculated based on all the sources. So then okay, let me just clean this part a bit here. So okay, we consider that all this overpressure source, they might happen, all this failure, they might happen simultaneously. So all these sources of pressure, they might accumulate together. So we always prepare or design the system, the flaring system, emergency system, based on the worst case scenario. Now, okay, about the overpressure, in which cases we can have overpressure. So this is kind of oil production, or it can be even gas production, that we take the gas from the well and we send it to the downstream process. It can be any type of equipment, separation, knockout drum. So if one of the very common cases is that the valves on the stream, they are blocked. They can be blocked with some solid particles, they can be blocked because of corrosion. It can have different reasons, but in case, if this happens, we have a blockage in this valve, there will be no flow through this pipe. So the pressure here will accumulate and we have to release it. we can design such a safety pressure relief system that includes one valve. So this means is like main electrical valve. So it's connected. This valve is connected to some electrical wire, electrical stream. So when the pressure here in this stream increases more than certain value, so this valve receive a message from the operator, and it will be open, and it will release some of this pressure and some gas to our relieving system. So this happens when there is a sudden closure of the valve in the flowing pipeline. So it can be for any reason. So in this case, the safety valve can provide a full flow rate from this valve. So this is one of the cases that we can use this pressure release valve to overcome the overpressure. Then heat exchanger tube failures. So we might have, okay, if you consider this heat exchanger system, that this is, let's say, my tube side. So I have a flow going to the tube side. It goes all the way through heat exchanger and come back from this part. Okay, so this is my tube side, and I also have, let me pick another color. I also have the shell side, which is usually from here, and it goes all the way through the shell, and it will leave from this part. So this is countercurrent, but we usually operate at countercurrent. So then, okay, so in this case, we usually have different pressure for the tube side and shell side. So let's say we are working in the case that the pressure in tube side is less than pressure in the shell side. Okay, pressure in the tube side is less than pressure in the shell side. Okay, this is what we have. So in this case, if we have a failure here, if the pressure, if you have a failure here, if you don't have enough pressure in this part, so we might have some operating problem. So in this case, we need to use a safety valve, okay, that can either relieve pressure from shell side, or we can have some kind of system to add pressure to the tube side. So we usually use this type of system when the pressure, let's say if tube side is less than the pressure in the tube side less than the shell side. So we usually do this when the pressure in the tube side is less than 2/3 of pressure in the shell side. This is, let me make it a bit cleaner. So we use this system when the pressure in the tube side is less than the pressure 2/3 of pressure in the shell side. So this is another way that we use pressure relief valve. Okay, utility failure. This is also very common in terms of, let's say, heat exchangers. So in heat exchangers, what we have, we receive vapor phase at the top, and we have a condenser here. This is my vapor phase. We have a condenser that condenses the vapor here and create a liquid. Then we have, here we have D, which is distillate or top product. Here we have liquid that goes back to the column, and we call it the reflux to the column. So this condenser works based on cooling water. We use cooling water here. We use cooling water. We use cooling water here to cool this stream, and then this cooling water, okay, if for any reason this cooling water failed, I mean the system that provides this cooling water for us, so it fails. So what will happen? The vapor here will be accumulated. We cannot condense this vapor and create liquid. So either it will be accumulated in the column, or it will be just recirculated to the column as a vapor. So it's a mal operation. So we cannot handle enough vapor, we cannot liquefy them, so the vapor accumulate. Once the vapor accumulate, the pressure inside the tank will increase. So we need to design such a pressure relief valve to purge the gas, the vapor in the distillation column. So, okay. So the pressure usually, if you don't have cooling water, the pressure starts to increase after 5 to 10 minutes that the cooling water is cut. So then we will have to adjust this valve to take action to purge this vapor. So that's another example of using pressure relief valve. So how we design such a pressure system? So there are some standards. So we select and design and choose these valves based on MAWP. What is MAWP? Maximum allowable working pressure of the process equipment. So let's say if we have our reactor here, if we have this reactor here, so what is the maximum allowable working pressure of this reactor that can help me to select and design this safety valve? So I will design it based on the maximum operating working pressure of this valve, and as well as how much temperature this reactor can tolerate, and what's the material of construction, if it's a steel, iron, whatever. So those are also important in selecting the valve. So, and the set pressure, I already talked about it. As I said, we have, let's say for this reactor, operating pressure is, let's say, 50 bars. Maximum pressure that it can undergo is, let's say, 100 bars. Then for the set pressure, means the safety valve that we have here, which we set the pressure of this valve something much below the maximum and little bit above the operating. Let's say set pressure can be something like about 70 bars. So when the pressure reaches to 70 bar, which is getting close to the maximum pressure and is above the operating bar, so this valve come to the action and it will open the line and it will purge some gas and reduce the pressure of our reactor. Then, okay, some additional information about the designing the flare system. So, once we consider all these equipments, the pressure set, the maximum capacity, worst scenario, we can do some kind of analysis that we call it final flare and relief analysis that has to be conducted to make sure that we respected all the safety aspects. Then, okay, worst case scenario has to be considered. We have to run kind of simulation or studies, comparative studies to consider the worst case scenario and see what will happen to our system. So the load of the flare is calculated based on the worst case scenario. Worst case scenario means we have all the type of failures, we have overpressure in all equipment, and this is how we calculate and design the capacity of our flaring system. Okay, so once we know the load of flare, we go design we design the network of the flaring system, which is the knockout drum, the liquid seal, the pumps, the network line, that is the network of piping that connects all the equipment to the flare header, and then to the knockout drum and flare. So we have to design that piping network, knockout drum, the pumps that we needed, and flare stack in terms of diameter and height. So this is some additional information about the flaring design, flaring system design. Now, okay, different type of, okay, flare stacks, so is another design parameter which is important. And the flare stack, it means this part here, this whole part. This is the flare stack. So the flare stack can be three types. It can be, this is important, it can be self-supported, that you see the stack is very strong, it's kind of big, it has a big diameter, it's kind of a strong body, so that it can tolerate its weight. We don't need any additional support to keep it stable on the ground and keep it straight, vertical position. This is one type. Another type is derrick supported. So we use kind of network of metal bars to keep the flare stagnant on the ground and in the vertical position. And the last type is guy support. Then we usually use this kind of wires connected to the ground to keep the flare stagnant. So we call it guy supported, and they use it usually for telecommunication antenna that you might have seen even in Qatar. We have this kind of antenna that we have to keep them stagnant. So this can be all this kind of method. This type of support can be also used for. Okay, next. Okay, the stack height. I mean the height of flare. How we calculate it. So this is also based on some standards, and we have to follow a standard for that. So the height, it means the height of flare means the distance of the top from ground. Okay, so this is the distance from ground. So we have to calculate this height from top. So the height of flare stack. So this is what we have to calculate it. So how let me just make it a bit cleaner. So this is the height from the ground to the top that we need to calculate. So if in calculating this, we have to consider few. There are several things that we have to consider. We have to consider few points. First, the thermal radiation intensity. It means how much flame we have at the top and how much thermal radiation it can produce. So then if there is more radiation, we have to put the flare tip to the higher level that in case there are like operators working on the ground, so they can get less affected by this. Luminosity, it means how much light it will produce, how much noise it will produce, and the height of surrounding structure. So there might be another column here, there might be reactor beside the flare, there might be other structures close to the flare. So how tall they are or how short they are, it can affect the design of the flare system. So that's another thing. And also the dispersion of exhaust gas. So exhaust gas, if it's dangerous gases, it's a very toxic gases, we have to release them at higher level to make sure that they never reach to the ground and they never get reach to the ground surface. So the flare height is designed by API PR 521. API is American Petroleum Institute standard that we use that guideline, which is based on mainly the radiation and dispersion of the exhaust gas. Then based on those guidelines, we can calculate the height of flare. Then, okay, some additional points about the flare height. Okay, so the radiation is one of the most important factor that determine the height of the flare. To calculate that height, we use a standard, is API RP 521. Usually this is also very important. This slide in general is important. So industrial flare, they are usually designed to handle heat capacity which is in heat equal to 1500 to 2000 BTU per hour square foot. So this is the amount of energy or the amount of, this is the heat value of the gas that they have to flare. So it's usually between this maximum capacity, and we will design the flare to handle this maximum capacity. And so if we are working, okay, if the flare is working at this level, at very high capacity, the workers that are working around the flare, they can remain in that area, but for limited time only, because the amount of exhaust gas that is produced, the amount of heat, the amount of noise can be harmful for the worker. So we don't want the worker to remain in that area for a long time. So only in a short period of time. And okay, however, if the capacity of the flare is much less, let's say is about 500 BTU per hour square feet, in that case the radiation is not that severe. So the workers, the operators, they can remain in the area permanently, for a longer time. So is not that much dangerous for them. So 500 is an acceptable one that the workers, they can work around, and but this one, 1500 to 2000 BTU per hour square foot, is very high, so the worker cannot stay there for a long time. Okay, the solar radiation is also in this range. The amount of solar radiation for the maximum capacity is about 250 to 330 BTU per hour square foot. So this is also the maximum radiation that we can have for a flare that is working maximum capacity, which is a big amount of energy. It's a big amount of energy that can affect the workers if they are working around. Then, okay. Another factor, not only the radiation, also the amount of the gas. So the amount of the vent gas. So let's say if we are not burning the gas, we are just sending the gas. We call it a cold vent. We are not burning. We just sending the gas to the flare. So it's really sometimes very toxic, very dangerous. So we have to consider that the amount of the gas that is going to be dispersed. And if we have more dangerous gas that has a higher flow rate, so we have to increase the height of flare. So how we calculate that? There are some modelings, there are some models, some equations, that is some standard that is used to consider the amount of gas, this gas dispersion, and then based on that they will design the flare height. Okay, so this is also important. The minimum flare height is normally 30 feet. This is also very important. The minimum flare height is usually 30 feet or about 10 meters. So cold vent, as I already explained, it can be in cases that we don't need to burn. We don't need to burn that vent gas. I mean, in the flare, we don't need to burn it. We just can release it as it is. So in that case, we don't have kind of flame. It is when the amount of relief gas is small. We don't have a big amount of relief gas or vent gas, okay, or so we don't really need to create a flame for that a small amount of gas or natural gas, so we can just vent it in the cold way without burning. So in this case, the gas should be mainly methane, okay, or natural gas should be mainly methane, which is a molecule lighter than air. The molecular weight of methane is much less than molecular weight of air. So in that case, we can make sure that is lighter and it can just go up, and the density is lower, so it can just go up, not come back to the ground surface. Then for the level of the flaring, we have to also design it properly to make sure that we flare all those gas out to the atmosphere. So it is used for when the flare system is connected to the atmospheric storage tank. We are going to talk about these tanks in the next slide. So the atmospheric storage tank is when we have when we have cold venting. So in this case, we don't have enough back pressure to the flare system. So don't have enough pressure for the flaring system to burn it or mix it with oxygen or air, any other combustible agent. And we can use some purge gas, but still, like, the amount of the gas won't be that much to burn it. So we can have cold. Okay, so in this photo, it shows some of this flaring system with refrigerated atmospheric storage tank. Atmospheric storage tank is a tank that works at atmospheric condition. Okay, and refrigerated means is kept at lower temperature. We usually do that to avoid any vaporization. So for designing this kind of tanks, we have to use the API 6500 650 standard, and then for the refrigerated atmospheric storage tank, for the design we will use API 620. So for atmospheric 650, refrigerated atmospheric 620.